Hey guys, this is going to be your 5.5 lecture. So 5.5 has two main topics, and the first we're going to cover pretty quickly, although we're going to run through it for the whole section, and that is the idea of an indefinite integral. And the other main idea in 5.5 is substitution. We actually, I think in one of the integrals in the last lesson, one of the definite integrals, I had to do a substitution, but I just kind of did it on the sly. The idea of an indefinite integral is we write the same symbols but without the limits of integration, and that's the notation for it. We actually say that the indefinite integral is the set of all antiderivatives, but because any antiderivative can be different from the others by at most a constant, we can write it as any particular antiderivative plus an arbitrary constant c. So real quick, an example of that, we'd say the indefinite integral of x dx equals 1/2 x squared plus c. So the integral of, or sorry, the antiderivative of x is 1/2 x squared, and then any other antiderivative is at most a constant different. Calc 1 students, especially calc students of all stripes, forget this plus c all the time. It is worth points. It is not worth all the points, but it is important that we remember when we take an antiderivative or when we take an indefinite integral. I'm going to use those phrases interchangeably usually, so I'll say we'll take an antiderivative as opposed to saying we'll take the indefinite integral. So that differs slightly from saying that it's everything, but really everybody knows what we mean. So the idea of an integral and an antiderivative are tied together really strongly. I do make a distinction when we're talking about a definite integral with limits of integration, but indefinite integrals and antiderivatives are at most different by a constant, so they are, and constants are practically invisible to us now, which is why everybody forgets to write plus c. The other main idea, let's start with a simple one here. Actually, I got a little room left on this page, is what if we had, I think this is the one that I ended up doing last time. What if I needed to find an antiderivative of cosine x dx? Well, we know the function that you take the derivative of to get cosine is sine x, so we just say sine x plus c. But now, what if there was a 2x in there? Well, what we can do is let u equal 2x. U is typically the letter we use for this. There's nothing special about u. Some books call this a u substitution. A lot of instructors call it a u substitution. That's the way I learned it, so I'm probably going to call it that at least some of the time. But if u equals 2x, then du equals 2 dx. And so if I plug this in, I get cosine of u, and then dx is actually 1/2 du, so times 1/2 du, and so that's 1/2 sine u plus a constant. And then the last step before we're done, making me wish I'd started further to the left here, I'm just going to use this blank space up here, is we have to plug back in. We can't leave the answer in terms of u. They asked us a question in terms of x. So we get 1/2 sine 2x plus a constant. So that's a u substitution, or just a substitution at its most basic. There are a lot, oops, I don't want to get rid of that entirely, I'll lose focus. There are a lot of different applications to this. For instance, and this is just an example from your book here, let's do the integral of x cubed plus x to the 5th times 3x squared plus 1 dx. Now we could do that integral by multiplying everything out and getting our polynomial in one long chain, integrating piece by piece. But if we notice here that if we let u equal x cubed plus x, then du equals 3x squared plus 1 dx, what we actually have here is u to the 5th du. I should mention, and your book spends some time talking about this, that all u substitution is the chain rule backwards. That is to say, well, let's get this antiderivative, and then I'll show you how that works. So then, if we integrate this, we get 1/6 u to the 6th, and then we back substitute, and so we plug in, and we have 1/6 x cubed plus x, that's what our u was, to the 6th. And then, oops, see, plus c plus c. Now if I start with this, if I start with f of x equals 1/6 x cubed plus x to the 6th plus c, and I take the derivative of this. Now, that was the end of the problem, just to clarify. I'm just showing you how this is the chain rule in reverse. Then I get 6 times 1/6, so I get x cubed plus x to the 5th times the derivative of the inside, which is where that 3x squared plus 1 comes from. Of course, the derivative of the plus c goes away. So that's what I mean when I say that u substitution, or just substitution, is just the chain rule in reverse. We've taken this piece and recognized that that came from our du dx, if you want to call it that. Let's do another example here. So let's take the antiderivative of 2x plus 1 dx. So here we have a case where this is not an easy integral to do unless we make a substitution. And so the goal of a substitution is to make it look like something we can integrate. So letting u equal 2x plus 1, then du is just 2 dx. We have to actually get that that means dx is 1/2 du to make this substitution. If I take a look at this, then that would make this the integral of the square root of u times 1/2 du. And now that's easy. That's 1/2 the square root of u to the 1/2 du. So we use our power rule for integrals, and so that's going to be times 2/3 u to the 3/2 plus c. And so that's 1/3. U was 2x plus 1, so that's 2x plus 1. Got to back our substitution off, to the 3/2 plus c. I don't like equal signs today for some reason. Your book has a statement of the substitution rule as a theorem. I don't think it's particularly helpful. However, the method is on page 344, and the steps are: let u equal g of x, whatever you decide, and then and du be g prime of x dx, and plug that in, and then integrate with respect to u, and then replace u with g of x again. So that's your basic steps. We're going to work some more examples though, don't worry. antiderivative of secant squared of 5x plus 1 times 5 dx. It's not a colon, that's a dot that got away from me. So we know the antiderivative of secant squared u. So it makes sense to let u be 5x plus 1. Then du is just 5 dx. And nicely enough, we even already have that, don't we? So then this is the antiderivative of secant squared u du. And the antiderivative of secant squared is tangent u, and then we need our constant. And so then we back substitute. We plug back in the 5x plus 1. So this is tangent of 5x plus 1 plus c. How about antiderivative of cosine 7 theta plus 3 d theta? Let's use a different letter here. Let's let t replace theta. So we'll let t equal 7 theta plus 3, then dt equals 7 d theta. So that means this is equal to 1/7 the integral of cosine t dt. I did not write this, but we could write d theta equals 1/7 dt. That's what I used to bring the 1/7 in. Antiderivative of cosine is sine, so this will be 1/7 sine t plus c, and then a little back substitution, 1/7 sine 7 theta plus 3 plus our constant. Let's see. How about antiderivative of x squared e to the x cubed dx? So this one looks a little different, and it might be hard to figure out exactly what you should use for your substitution. And your clue should be the relationship here between x cubed and x squared. So if I let u equal x cubed, then du is 3x squared, and I have that piece. If I had let u be all of e to the x cubed, then it might not have gone so well for me, or if I had done something else. So noticing that this x squared would be part of my du if I let u equal x cubed was kind of the key to knowing which substitution to make. So u is x cubed, du is 3x squared dx. So x squared dx is what I have there, and that's equal to 1/3 du. This last step here, this is optional. It's helpful when you're first doing it, but once you get the hang of it, you may not write that every time, and it's just fine. I do recommend that until you get a real firm grasp on these substitutions, you do write down u and du, though. So plugging in, this becomes the integral of e to the u, and I need a 1/3 and then a du. So then taking an antiderivative here, I get 1/3 e to the u plus c, and then I plug back in, so this is 1/3 e to the x cubed plus c. This next one is really similar. The square root of x times the square root of 2x plus 1. If we could do this several different ways. We could say, or we could try this several different ways. U equals the square root of 2x plus 1. If we try that now, du equals, what is that? That's going to be 2 over 2 times the square root of 2x plus 1, right? Those will cancel. So 1 over the square root of 2x plus 1 dx. And I don't have that piece. So that's not a good substitution for us. What if I let u be equal to 2x plus 1, though? Then du is equal to 2 dx. And the only thing that gives me trouble on is, what do I do with this extra x? Well, the extra x, we can actually figure out what it is in terms of u by using our original statement. So 2x plus 1 equals u, x equals u minus 1 over 2. I kind of got a little focus issue here. Let's see if we can't bring that in. Oh, it's just a little fuzzy though. Sorry about this. Maybe it'll come into focus here in a second. I think it likes the top of the page too much though. So we can replace x with u minus 1 over 2. We can replace 2x plus 1 with u. And we can replace dx, oops, I never wrote dx, with 1/2 du. So putting that all together, we have 1/4 the square root of u times the square root of u is u to the 3/2 minus u to the 1/2 du. So I can now take my antiderivative term by term. I get 1/4. The antiderivative of u to the 3/2 is 2/5 u to the 5/2. And the antiderivative of u to the 1/2 is 2/3 u to the 3/2 plus my constant. Now, all I need to do here is back substitute. U is equal to 2x plus 1. So this is 1/4 times the quantity 2/5, 2x plus 1 to the 5/2 minus 2/3, 2x plus 1 to the 3/2 plus c. Let's see. Let's try, I did something like that one. Let's go ahead and try antiderivative of tangent x dx. So I don't think we have this one. I don't think we had anything that had tangent as a derivative. So I don't think in your catalog of functions you just have this ready to go. So let's talk about how we can get there. What if we use the trig identity and write this as sine x over cosine x dx? Then we can let u equal cosine x, then du will be equal to minus sine x dx. And so this becomes the integral of minus du over u, which is minus the natural log of u. We need absolute value bars around our u, plus our constant. And so then when we back substitute, we get minus the natural log of cosine x plus c. We can rewrite that. Remember, tangent and secant play well together. There's nothing wrong with leaving the answer in this form, but just because tangent and secant play well together, it might be nice to remember that if I use my natural log property, I can write this as the natural log of 1 over cosine x plus c, which is the natural log of secant x plus c. Let's try this one. How about antiderivative of 2z dz over the cube root of z squared plus 1? So there's a couple of ways to do this one, and there actually are not just one way that doesn't work and one way that does. We could let u be equal to z squared plus 1. Then du is equal to 2z dz. This is probably the most straightforward way. So then we get du over u to the 1/3. I prefer to write that as u to the minus 1/3 du. So the antiderivative here, that's going to be 3/2 u to the 2/3 plus c. And when we substitute back in, we get 3/2 z squared plus 1 to the 2/3 plus c. Another way we could do this one is we're going to start with the same thing, 2z dz over the cube root of z squared plus 1. So if we let u equal the cube root of z squared plus 1, then du is equal to 2z over the cube root of z squared plus 1 dz. I think I have that right. Nope, not quite. Not quite. That should have been a 2/3. That throws everything off. Instead, we can say u cubed equals z squared plus 1, which means that 3u squared du equals 2z dz. So I can replace the denominator with u and the numerator with 3u squared du, which is just the antiderivative of 3u du, which is 3/2 u squared plus c, which is 3/2 z squared plus 1 to the 2/3 plus c. Like I said, I think this is the more straightforward way to do it, but there are some occasions where the second substitution makes just as much sense. Let me know if you guys have any questions.